Okay, Chapter 5 is logarithmic, exponential, and other transcendental functions. Hopefully you did most of Chapter 5 in Cal 1, but we're going to back up and do sections 1 through 6 again. And as you can see, I kind of condensed sections 1 and 2 into one thing of notes. It's the natural log function, both differentiation and integration. Okay, some review. Properties of the natural log function. The natural log function is defined by ln of x equals the definite integral from 1 to x of 1 over t dt, where x has to be greater than 0. That's how you define it with calculus. We're going to come back to that in a minute. Okay, let's go do some pre-cal review. The natural log function has the following properties. Okay, going over here, y equals ln of x. Your three favorite y values are -1, 0, and 1. What are the x values that correspond to those three favorite y values? Ln of e is 1, right? Ln of 1 is 0. And ln of 1 over e is -1. Usually when I introduce the log function, you do the exponential function first, and you see that exponentials and logs are inverses of each other. But this is how the book does it, so this is what we're going to do. Okay, let's go plot those 3 points. 1 over e is about, I want to say 0.37. Is that right? And e is approximately 2.81828, so say 2.8. Okay, so you have the point 0.3, -1, 1, 0, and 2.81. So the natural log function looks like this. Coming back from college algebra? Okay, what is the domain of the natural log function? What x's can you plug in? Anything that's bigger than 0, because there's a vertical asymptote where? On the y-axis. So the domain in interval notation is going to be 0 to infinity. What about the range? What y values get spit out? Negative infinity all the way up to positive infinity. So all real numbers. Okay, another property, it's continuous. When you draw that function, you never pick up your pencil. It's continuous, it's always increasing. What does always increasing mean in terms of calculus? What about that first derivative? If a function's always increasing, the first derivative is always going to be positive, right? So I might make note that means that f prime is always greater than 0. And that function is 1 to 1. How do you know it's 1 to 1? It passes the horizontal line test. Anytime you draw a horizontal line, how many times is the horizontal line going to pass through that function? Just once. And if that's the case, then the function is 1 to 1. If the function is 1 to 1, it has an inverse function. We're going to get there in another section. It's concave. Which way? Concave up or concave down? It's always concave down. If you know that it's concave down, then you know the second derivative is always what? Negative. It's always going to be less than 0. Perfect. All right, another theorem. If a and b are positive numbers and n is rational, what's the natural log of 1 always equal to? 0. Okay, the natural log of a product, the natural log of a times b, you can split that up as the sum of two natural logs. It's natural log of a plus the natural log of b. The natural log of a raised to the n power, that power can sprout legs and walk out front, so you get n times the ln of A. The natural log of a quotient, natural log of A divided by B, you can also split that up as ln of A minus ln B. Those are college algebra, algebra 2 from high school properties. We're going to use them. Okay, another definition. The irrational number E denotes the positive real number such that the ln of E is the definite integral from 1 to E of 1 over t dt. And it gives you 1. It's an irrational number. It's approximately equal to 2.71828. Oops. So back here, I should have put 2.7 right there. .71828. Okay, derivatives of the natural log function. Anything in red, by the way, is either going to be a rule or a theorem. Red denotes pretty much you need to know it. You need to kind of commit it to memory. You're going to be using it. This is one of those times. Okay, if y equals ln of x, the derivative is 1 over x. If y equals the natural log of some function of x, ln of u, you're going to do 1 over u, whatever you're taking the natural log of, do 1 over that. And then you have to say times the derivative of that. We're going to go do several examples right now. So the derivative of ln blah is 1 over blah times the derivative of blah. 1 over blah d blah. Here we go with the first example. Find the derivative of y equals natural log of 1 minus x. So I'm going to tell you the derivative is 1 over, what are you taking the natural log of? 1 minus x. Times, now what's the derivative of 1 minus x? Almost. What's the derivative of negative x? Negative 1. So I would write it as negative 1 over 1 minus x. If you want to write it as 1 over x minus 1, by all means, go for it. I've learned, don't try to showboat and clean stuff up when you don't have to. Just leave it alone. Let it be right and be done. Okay, what about natural log of 5x? The derivative is 1 over 5x times, derivative of 5x is just 5, so what happens to the 5's? They cancel, so you're left with 1 over x. Now, to do number 2 a different way, you agree with me that the natural log of 5x can be written as ln of 5 plus the ln of x. You agree? Now, what's the derivative of ln 5? ln 5 is just a number. The derivative of a number is just 0. So I get 0 plus derivative of ln x is 1 over x. It's the same thing, right? Same answer? Good. Whew. Did it right. You probably aren't going to think that way, though. You're going to think the way in the blue. All right, number 3. What do you notice up there at the top? There's an exponent. What can that exponent do? Move it out front first. So I'm going to tell you, rewrite that as 2 times the ln of x plus 1. Otherwise, when you take the derivative of this, you're going to have to do the chain rule. 2 times x plus 1 to the 1 times 1. That gets messy. Try to avoid that stuff. Move the 2 out front first. All right, now what's the derivative? 2 times derivative of ln x plus 1 is 1 over x plus 1 times 1. So I would probably clean it up and say 2 over x plus 1. Now, I just told you that exponent, you wanted to move it out front, so go look at number 4. Do you see an exponent?
Yes.
Yes, it's 1/2. So I'm going to rewrite this as 1/2 times ln of x squared minus 4. Square root, you can write it as that stuff to the 1/2 power. Bring the power out front. So the derivative will be 1/2 times derivative of ln blah, 1 over blah, times, now what's the derivative of x squared minus 4?
2x.
Just 2x. Now the 2's will cancel. And you're left with x over x squared minus 4. Not too bad? Does it get harder? No, it gets more fun. All right. Using properties of logs, how would I rewrite that? That's the natural log of a quotient.
ln
2x minus ln x plus 3.
You got it. Split it up. ln 2x minus ln of x plus 3. Use the properties of logs before you start taking derivatives, if at all possible. All right, when we take the derivative of number 5, I get y prime equals 1 over 2x times the derivative of 2x, which is 2, minus 1 over x plus 3 times 1. Derivative of x plus 3 is just 1. 2's will cancel. I'm left with 1 over x minus 1 over x plus 3. Okay, do you notice that my fractions, I do a numerator on one line and a denominator on the next? Which direction is my bar? It is horizontal. For those of you who do a slanted bar, shame, 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 get out of that habit. Do a horizontal bar for your fractions. I am as OCD as they come with math, and it's for a reason. How many of you do equal signs and you go across the page? Something equals something equals something, and you go, don't do that. Go down. I'm going to give you some good habits to get into, and it will probably drive some of you crazy. I apologize in advance. It's me. All right, number 6. Y equals x squared times ln x. Did you hear the word times? What rule am I going to have to use? Product rule. I have a first function and a second function. Product rule says derivative equals first times the derivative of the second plus the second times the derivative of the first, right? Okay, so here we go. Product rule is first, which is just x squared, times the derivative of the second, 1 over x, plus the second, ln x, times the derivative of the first, 2x. Yes? So I'm going to put a note out here. If it's been a while since you've had math or been a while since you've had calculus, product rule. Okay, can I simplify that and clean that up any? X squared over x gives me just x plus 2x ln x. Usually you want to write the constant and variables in front of the ln's or the trigs. Questions on that? First times the derivative of the second plus second derivative of the first. All right. Question? Okay, number 7, when I look at it, y equals natural log of the natural log of x. What's hidden in that? You're going to have to use the chain rule, because I'm taking the ln of something. This something, right? So when I take the derivative, I'm going to do 1 over blah. What's my blah? ln x times the derivative of blah. What's the derivative of ln x? 1 over x. So I'm going to rewrite it and write 1 over x ln x. Get the rule down to take the derivative of natural log blah. It's 1 over blah times the derivative of blah. All right. Another theorem. Let u be a differentiable function of x. So this is when you're taking the derivative of natural log of absolute value of something. So if y equals a natural log of absolute value of x, guess what the derivative is? It's just 1 over x. It doesn't matter if the absolute value is there or not. So if u is a function of x, natural log absolute value of u is going to be 1 over u times u prime. So some examples. Find the derivative. Y equals natural log absolute value cosecant x. Do those absolute values, does it really matter if it's there or not? No. Same rule. Okay, y prime equals 1 over cosecant x, oh boy, times derivative of cosecant x. It starts with a c, so I know it's negative. Negative. Okay, here we go. You ready? Here's y prime. Let's go do it in orange. Y prime. Derivative of sine x is cosine x. Derivative of cosine x is negative sine x. Derivative of tangent x is secant squared x. Derivative of secant x is secant x tangent x. Ooh, I ran out of room. Derivative of cotangent x is negative cosecant squared x. And derivative of cosecant x is negative cosecant x cotangent x. Notice everything that has a c, cosine, cotangent, cosecant, when you take the derivative, guess what? You get a negative. Did y'all see that relationship last semester? Okay, so the derivative of cosecant x is negative cosecant x cotangent x. Now, the cosecant x's will cancel, and you're left with negative cotangent x. Okay, all the stuff in the orange, guess where it is? It's on your formula sheet. It's there. But that's something that you should be able to do. Now, I took Cal 1 back in probably before y'all were born. I still, to this day, if I have to do secant or cotangent or something, I still go through this list in my head. I do it quickly, but I still go through that list. That's how I memorized it. All right, last one. Y equals natural log absolute secant x plus tangent x. Y prime equals 1 over secant x plus tangent x times the derivative of secant, which was secant x times tangent x, plus the derivative of tangent, which was secant squared x. Are you using parentheses when you're doing times the derivative of? Especially when you've got a sum. Make sure you've got parentheses around that. All right, what can I factor out up top? A secant x. If I do, I'm left with a tan x plus a secant x. And guess what was on the denominator? Secant x plus tan x. So that is going to go away. The answer is just secant x. I'm going to stop it here and do another recording for letter C.